All right, now that you guys have learned about exponent rules, we're going to talk about solving exponential equations using a method specifically called looking inside. So if I have an equation like 2 to the 5th equals 2 to the x power, so we don't know what this is raised to. Looking inside, the idea behind it is I know that 2 to the 5th is the same as 2 to the 5th. That would make this equation true. And so 2 to the 5th has to equal 2 to the 5th. That means that x has to equal 5. So the idea of looking inside is because these bases are the same, I can just kind of ignore them. I can kind of cover them up and just look at the exponents and know that the exponents have to be equal because 2 to the 5th has to equal 2 to the 5th, so x has to equal 5. So you can kind of skip this step here and you can just say, oh, I can just look inside the exponent and say that x equals 5. All right, let's do another one. Now in this case, our exponents are the same. Something to the third equals 7 to the third. Well, because the exponents are the same, I know that the bases need to be the same for this equation to be true. So I can look inside the bases this time and know that x equals 7 because they're both being raised to the third power. All right, so that is the basic idea of looking inside. Let's do a couple more where it looks a little more complex. All right, we got 2 to the x plus 3 equals 2 to the 2x. Notice that both the bases are the same, so I know that 2 raised to whatever power has to equal 2 raised to the same power, so I can look inside my exponents and just set my exponents equal to each other. Looks like I got an equation where the variable is on both sides, so we want to remember our first step is to move our x's together. So I'm going to move my x over here to the other side. This makes a zero pair. Remember that. And 3 equals 2x minus 1x is the same as just 1x or x. So I know that x equals 3. All right, let's do one more example. Here we got 3 to the 2x plus 1 equals 3 to the third. Again, the bases are the same, so I can look inside the exponents, knowing that these have to be equal to each other for this equation to be true. And then from here, we just tell the story of x. Looks like x is being multiplied with 2, and then 1 is being added with it. So let's reverse it. I got to undo a plus 1, so I'm going to minus 1. Rewrite it. We got 2x equals 2. Then I got to times 2, so I'm going to undo that by dividing by 2 on both sides. This makes a 1, and 1 times x is just x equals 2 divided by 2 is 1. You can't always check your answer, which is nice, so I could plug this back in, and we can check. Does 3 to the 2 times 1 plus 1 equal 3 to the third? Question mark. 2 times 1 is 2, plus 1 is 3, so 3 to the third does indeed equal 3 to the third, and we know that that works.
Alright guys, now we are going to look at an equation that looks something like this. So in this case, we have two numbers where the bases are not the same. So we can't look inside like we did on the previous example. So our goal here is to make it so our bases are the same so that we can solve for x. This right here, our base is 6, and we have 6 to the power of 8 times x, and our base here is 36. So we're going to try to see if we can rewrite 36 to have a base of 6 with some exponent. So if we make the base 6, 6 to what power is going to give me 36? Well, I know that 6 squared, or 6 to the second power, gives me 36. So I can rewrite this as 6 squared and then keep this one the same. So now I have 6 to the 8x equals 6 squared. So now, as you can see, I have two bases that are the same. So I can look inside here and make 8x equal to 2. And then I can solve for x by doing the opposite here. We have 8 times x, so I'm going to do 8 divided by 8 on this side, and that becomes 1. And then 2 divided by 8, and we can simplify that to be, if you divide both sides, both parts of the fraction by 2, then you get 1 over 4.
All right, in order to solve this exponential equation, we see that the bases are not the same here. So we'll have to do what Emma showed us, where we need to rewrite the larger base in terms of the smaller base. So I want to turn this 9 into 3, because I want them to have the same base, 3 to the something power. I need to know how many times do I need to multiply 3 in order to get 9. So off to the side here, I'm just going to do like 3. Okay, I know 3 isn't quite 9. Okay, let's do times 3. 3 times 3 is 9. So I know that I can rewrite 9 as 3 squared. Because this is also all being raised to the 2x, it's very key that I put parentheses around this, because all of this, like all of 9 is the same thing as 3 squared, and all of that is being raised to the 2x. So we got 3 squared to the 2x power equals 3 to the 5th. If we remember our exponent rules, I can distribute this exponent here. And so this is the same as 3 to the 5th equals 3 to the 4x. And now I can look inside and say 5 is the same thing as 4x. And then we can divide both sides by 4. And we are left with x equals 5/4. And in Derivita, if you do get a fraction answer, you can just leave it. If you try typing it as a decimal, it might not say it's correct because you may have rounded your decimal.
So now we're going to look at an example like this. We have 8 to the 3rd equals 2 to the x plus 1. So like we have done in the past couple examples, we want to get these bases to be the same. And so we want to change this 8 to have a base of 2. So if we look at 8, we can just write it as a base of 2, and we want to know what power does it have to be raised to? How many times do we have to multiply 2 by itself to get 8? If we start over here, we have 2, that's not quite 8, times 2, 2 times 2 is 4, not quite 8, times 2, one more, 2 times 2 is 4, times 2 is 8. So we know that 2 times 2 times 2, or 2 to the 3rd, is the same thing as 8. Okay, so now we have 2 to the 3rd, which is the same thing as 8. Like Tiana said in our last example, we have to make sure that this stays in parentheses and that we keep this exponent that was already here, because 8 is being raised to the 3rd here, so that means that 2 to the 3rd has to be raised to the 3rd. And this will equal 2 to the x plus 1. So now when we use our exponent rules, we know that we can multiply 3 times 3. So we have 2 to the 9 equals 2 to the x plus 1. And we can kind of ignore our bases since they're the same. We have 9 equals x plus 1. And so now if we solve the equation, try to get x by itself, we do the opposite of adding 1, minus 1 from both sides, and we get that 8 equals 6.
All right, we got 2/3 to the x equals 8/27. Remember when I have parentheses that this exponent is applying to both pieces of my fraction? So another way you could write this is 2 to the x over 3 to the x. X has to be the same number though, and has to give me 8/27. So in order for this to work out, we got to express 8 in terms of 2 and 3 in terms of 27, and we want to make sure that it comes out the same. So with 8, if I want to express it in terms of 2, or not quite 8, times 2 is 4, not quite 8, times 2, okay? 4 times 2 is 8, and so I know that 2 has to be raised to the 3rd power in order to be 8. Let's make sure it's also 3 iterations for the bottom of our fraction. So 27, I want to express that in terms of 3. 27, we got 3, times 3 is 9, not quite 27 yet, times another 3 is 27, so yes, 3 to the 3rd power is also 27. So I can rewrite this as 2/3 raised to the 3rd power equals 8/27. I know that x has to equal 3 because it took me 3 iterations of 2 to get 8 and 3 iterations of 3 to get me 27, and it is the same for the top and the bottom.
All right, so now we have this equation, 7/3 to the power of x equals 9/49. So if we remember from the last example, when we have a fraction raised to an exponent, this exponent is applied to both the 7 and the 3, the top and the bottom of my fraction. So I can think about it the same way we thought about it on the last one. 7 to what power is going to give me 9? 3 to what power is going to give me 49? So if I start with 7, I can make a list over here. 7, not quite 9, okay? 7 to the 1st power doesn't give me 9. 7 to the 2nd power, so 7 times 7 equals 49. So that's way too big. So there's not a whole number that I can raise 7 to that will give me 9, because 7 to the 1st power is too small, 7 to the 2nd power is way too big. But if we notice, 7 to the 2nd power got me 49, and I have a 49 here in the denominator of this fraction, okay? We'll just hold that thought for a second. All right, so now let's look at the 3. 3 to what power is going to give me 49? All right, 3 to the 1st power is 3, so I'm not quite there. 3 to the 2nd power, 3 times 3 equals 9. And I'm going to stop right there because this 9 matches this 9 right here. So if you remember back to our exponent rules, if we raise any base to a negative number, it's going to flip the fraction. So we know that we had to do 3 times 3, so 3 squared to get 9, and 7 times 7, or 7 squared to get 49. So we know that if we do 7/3 raised to just the 2nd power, that would give me 49/9. But that's not quite what I want. I want it to be 9/49. So what I can do is instead I can say 7/3 raised to the -2 power, and that is going to flip my fraction and give me 9/49.